What if Google's Willow quantum chip did not simply perform a faster calculation, but briefly touched a part of reality we were never supposed to access? In December 2024, Google announced a quantum processor capable of completing a benchmark in minutes that would take the most powerful classical supercomputers an almost impossible amount of time to reproduce, far longer than the age of the universe itself. But the most disturbing question was not how fast the chip was. The real question was where that computation was happening. Because when a quantum computer operates, it does not behave like an ordinary machine moving through one simple path of zeros and ones. It works through superposition, entanglement, and interference, exploring a vast space of possibilities that seems far too large to fit inside a small chip sitting in a laboratory. That is why some physicists have started pointing toward one of the strangest ideas in science, that quantum computation may be drawing power from parallel branches of reality. Not as science fiction, but as a serious interpretation of what the mathematics may actually mean. Willow is not large, dramatic, or visually terrifying. It does not look like a portal, a starship engine, or a machine built to tear holes in space. At its core, it is a quantum processor with 105 qubits, carefully isolated and cooled to temperatures so low that ordinary environmental noise is almost forced into silence. But what it accomplished was extraordinary. In a benchmark known as random circuit sampling, Willow produced a result in under 5 minutes that Google estimated would take a leading classical supercomputer around 10 septillion years to reproduce. That number is so enormous that it almost stops behaving like a number and becomes a warning, because it points to a type of computation that does not seem to belong in the same category as ordinary computing. Classical computers calculate through bits, each one fixed as either 0 or 1. Quantum computers, however, use qubits, which can exist in combinations of 0 and 1 until they are measured. When many qubits become entangled, the system can represent an enormous number of possible states at once, creating a computational space that grows faster than human intuition can follow. That is where Willow becomes unsettling. If a tiny chip can process a space of possibilities larger than anything a classical machine could realistically track, then the natural question is not simply how fast it is, but what physical reality is actually doing while the computation unfolds. Because the answer may not be contained entirely inside one ordinary universe. The idea of parallel universes in quantum mechanics comes from the many-worlds interpretation, first developed by Hugh Everett in the 20th century and later taken seriously by major thinkers in quantum computing, including David Deutsch. In this view, the wave function is not merely a mathematical tool for predicting probabilities, but a real description of reality itself. Every possible quantum outcome does not collapse into one chosen result. Instead, reality branches, and every outcome happens in its own version of the universe. This sounds wild, but it comes directly from taking the equation seriously. In the traditional view, when a quantum system is measured, many possibilities somehow become one outcome, although the exact physical meaning of that collapse remains deeply unresolved. In the many-worlds view, there is no collapse at all. The wave function keeps evolving, and the different outcomes simply separate into branches that no longer interact in ordinary ways. Quantum computing makes this interpretation harder to ignore because a quantum machine appears to process many possibilities simultaneously. When the result emerges, it looks as if different branches of the calculation have interfered with each other to guide the final answer. That is the strange word at the heart of the discussion: interference. Not interference like a bad radio signal, but quantum interference, where possible paths combine, cancel, and reinforce one another until the correct pattern becomes visible. If the many-worlds interpretation is correct, Willow may not be calculating only here. It may be exploiting the structure of many parallel branches, allowing possibilities from different versions of reality to contribute to a single result in our own. To understand why this matters, imagine trying to solve a maze by walking one route at a time. That is how a classical computer behaves. It can move incredibly fast, but it still has to process information through definite steps, one logical operation after another. A quantum computer behaves more like a system that explores many possible routes at once, allowing wrong paths to cancel and useful paths to reinforce each other through quantum interference. The result is not magic, but it is profoundly strange because the machine is using the deep structure of probability itself as part of the calculation. This is why Willow's benchmark attracted so much attention. It was not solving an everyday problem like designing a battery or discovering a new medicine. Instead, It demonstrated that a quantum processor can generate patterns that are effectively impossible for classical systems to reproduce within any reasonable amount of time.